Hello, here are our video notes for section 6.2. This section can be kind of a doozy, not gonna lie, but you just got to think about the properties that you know and just apply them to rational exponents. People will freak out because of the fractions. Don't do that. Um, let's review these properties. We know that when we're multiplying powers with like bases, we keep the base and we add the exponents, okay? What this looks like with rational exponents is something like this. Let's say that we had 5 to the 1/2 times 5 to the 1/3. We know that we're going to keep the same base and add 1/2 plus 1/3. Only thing is that because of the fractions, we have to create common denominators for those, and then we can add them. So that's the thing that makes this section a little bit different, is we've just got to think about common denominators. The common denominator of 2 and 3 is 6. 1/2 is equivalent to 3/6, 1/3 is equivalent to 2/6, then you can add them together, all right? We know that when we have a power raised to a power, we multiply the exponents. So if we had something like 5 to the 1/2 raised to the 1/3, we know that that's like 5 to the 1/2 times 1/3. And the nice thing about multiplying fractions is that you just multiply the numerators 1 times 1, multiply the denominators 2 times 3, and we get 5 to the 1/6. When we have the power of a product, we apply that exponent to both of the factors. So if you had something like 8x to the 1/3, you would think about that as 8 to the 1/3 and x to the 1/3. But remember from our other lesson that 8 to the 1/3 is really like the cube root of 8, and we know that the cube root of 8 is 2, so we would simplify that to 2 times x to the 1/3. Remember, when we have a negative exponent, we bring that exponent to the denominator, and so if we had something like 5 to the negative 1/2, that would be like 1 over 5 to the 1/2, and then we would simplify it from there. I'll just write then simplify for right now. We'll practice that later. But in general, when you have negative exponents, we move them over the fraction bar, they turn into positive exponents. Okay? When we're dividing powers, we keep the base and we subtract the exponents. So if we had 5 to the 1/2 divided by 5 to the 1/3, that's going to be like 5 to the 1/2 minus 1/3. Again, we can keep the bases the same. Base the same. We subtract the exponents, we make a common denominator, and then we just simplify from there. If you need help with common denominators and fractions, come after school. If we have the power of a quotient, again, we apply the exponent to both the numerator and denominator. So if we had x over 8 to the 1/3, then that's like saying x to the 1/3 over 8 to the 1/3. Again, remember 8 to the 1/3 is like the cube root of 8, which is 2. So we would have x to the 1/3 over 2. And this is something that we had before with a property of radicals that you had before. If you had the square root of a times b, you take the square root of each one. So that's the same with the nth root. If you have the nth root of a times b, you can simplify that into the nth root of a times the nth root of b. So here's how we do that. Let's say that you have the cube root of 40. When we were simplifying square roots, we used to look at perfect squares that go into 40. But now, because we're looking at the cube root, you want to think about perfect cubes. Well, 1 goes into everything, but like 8, 27, 64. And we could have stopped earlier because 8 goes into 40, doesn't it? 8 is a cube root that goes into 40. So we're going to think about writing this as the cube root of 8, and it's 8 times 5, that's 40. So we're going to break this cube root of 40 down into the cube root of 8 times the cube root of 5. And the cube root of 8 is 2. That's why we chose 8. And the cube root of 5 has no other cube roots in it, so it's stuck under the radical. Let's say we have the nth root of a over b. Again, we can just take the nth root of the numerator and the denominator. So if we had the cube root of x over 8, that would be like the cube root of x over the cube root of 8. And then the nice thing is that the cube root of 8 is 2, so that's simplified. Okay? So example 1 asks us to use the properties of rational exponents, which are just like the properties of exponents, to simplify the expression. So if we have 12 to the 1/8 times 12 to the 5/6, that means we're going to want to add the exponents. So what's going to happen, you could write it like this if you want, 12 to the 1/8 plus 5/6. But we're going to need a common denominator, aren't we? Let's see, the lowest common denominator of 8 and 6 is 24. I like to think about multiples of the larger denominator and then see when does the other denominator go into it. So like 8 doesn't work. 8 times 2 is 16. 6 won't go into 16. 8 times 3 is 24. That works. Okay? Again, if you have trouble with the fractions, let me know. So 1/8 is equivalent to 3 24ths. 5/6 is equivalent to 20 24ths. So what happens is when I add those exponents, I end up getting 23 24ths. So my base is 12, my exponent is 23 24ths. Looking at letter B, 5 to the 1/3 times 7 to the 3/4. Well, I want to apply this exponent to the 1/3. So I think 1/3 times 3, well, that just gives me 1. And then 1/4 times 3, well, that gives me 3/4. So I have 5 to the 1st, or just 5, times 7 to the 3/4. That's all I can do with that one. I can't multiply the 5 and 7 because 5 doesn't have that same exponent, so I'm stuck there. Okay? Let's look at C. C, we have 2 to the 6 times 4 to the 6 to the negative 1/6. Well, let's apply this exponent to each of these. And 6 times negative 1/6 is negative 1. Again, 6 times negative 1/6 is negative 1. And then I have 2 to the negative 1 times 4 to the negative 1. Well, I can't do operations until I get rid of these exponents. 2 to the negative 1 is like 1/2. 4 to the negative 1 is like 1/4. And I can multiply those together and I can get 1/8. Let's talk about letter D. We have 10 over 10 to the 2/5. Now, remember that this is like 10 to the 1st and 10 to the, and we want to subtract these exponents. Well, maybe we should think about that exponent as 10 to the 5/5. Isn't 5/5 1? And the reason I would do that is because if in the denominator I have 10 to the 2/5, essentially what I'm going to be doing is I'll be subtracting this 5/5 minus 2/5. And that gives me 10 to the 3/5. And again, you don't have to write this step, or you could write it differently, but as long as we get to that answer of 10 to the 3/5. In letter E, I have 56 to the 1/4 over 7 to the 1/4 to the 5th. And one thing I notice about this is that these are both raised to the 1/4 power. And so what I am going to think about doing in this case is kind of using the reverse of this quotient property. And I'm going to realize that this is really the same as 56 over 7 to the 1/4. Then if I applied the 1/4, I would have gotten this. That being said, what this is really saying is that that's like 8 to the 1/4. So I'm going to try to think about it like this instead. 8 to the 1/4 to the 5th. Now I know I can multiply these exponents, and that gives me 8 to the 5/4. And the thing is that this looks like it's the final answer, but one thing that I notice about 8 is that 8 can be written with a smaller base. Okay. So let's make a note. 8 can be written with a smaller base. And getting into this habit of writing a number with a smaller base is going to be helpful to us going forward. when you think about 8, hopefully we're using our chart and we're seeing that 8 really is the same as 2 cubed. And so what we can do then is now multiply these exponents to get 2 to the 15/4 as our final answer. You might say, well, why didn't we do that in the other problems? Well, 12 can't be written that way. 5 can't be written as a smaller power, nor can 7, nor can 10. And here, this 8 was not being raised to anything. So anyway, we'll work through that while we do the homework in class. So those are some examples. All right, number 2, let's say they give you a story problem. It says the ratio of magnitude of 2 earthquakes with magnitudes M1 and M2, if you measure it on a Richter scale, is given by this equation. Here are some of the magnitudes, and it wants to know how many times stronger was the 1964 earthquake in Alaska than the 1812 earthquake in Missouri. So basically, to find these values, it wants us to take the 1964 Alaska value and divide it by the 1812 Missouri value. So if we look at the 1964 Alaska value, it was 9.2. And notice that's going to be the exponent that we use. So we'll take 10 to the 9.2 over, and now 1812 Missouri was 7.9. 10 to the 7.9. We can see that these have the same base, so we can keep the base and subtract the exponents, and we get 10 to the 1.3. Well, I don't know what that is, so when it says how many times stronger is it, let's find what that is. Let's just take 10 to the 1.3, and notice that that means that it was almost 20 times stronger. Because I know we don't talk like that. Oh, it was 10 to the 1.3 times as strong. That's silly. But about 20 times stronger. All right? All right, let's flip to the back. When we simplify these expressions, if it can be simplified all at once, simplify it. So for example, if we see the cube root of 125, we look at our chart and we see, oh my gosh, 125 is a perfect cube. This is so exciting. That's 5. And the cube root of 8, that's 2. So don't let problems like this escape you. Those are really nice. Let's see what happens in letter B. Again, this looks like a hot mess, but notice these have the same index. And again, we're going to use the opposite of this right here, where if we have the nth root of the same nth root of two different values, we can turn it into the nth root of a quotient. So it's like we're going backwards with this rule. So if we look at this, this is going to be like the 5th root of 96 over 3. And so then this ends up being the 5th root of 32 if we divide 96 by 3. And the cool thing about the 5th root of 32 is that that ends up being 2. So that's happy. Okay, so look for opportunities for us to use those perfect cubes, those values in the exponents we should use in those powers. Okay, so remember, a radical with index n is in simplest form if the radicand has no perfect squares or as factors and there are no radicals in the denominator. So instead of perfect squares here, we're going to be looking at perfect cubes, perfect fourths. So if I look at example A, the cube root of 104, I want to look for perfect cubes. So again, because it's this cube root, I'm going to look for numbers like 8, 27, 64. So maybe I'll just start with 8. I don't know if 8 goes into 104. So here, let's look. 104 divided by 8 is 13. Awesome. So that means I could break 104 down into the cube root of 8 and the cube root of 13. Well, we picked the cube root of 8 because that's 2. 13 doesn't have any of these that go into it, so we keep it as the cube root of 13. Now let's look at the cube root of 432. Well, again, I'm going to need to look for different perfect cubes. And I look on my perfect cube chart, and I see these different values. And one thing that I notice is that 432 looks like it's 216 doubled. So I'm going to break that down into the cube root of 216, and 432 would be 216 times 2. So the cube root of 216 is 6. 2 doesn't have any other cube roots. We're all set. Now I just want to point out to you that maybe you wouldn't have seen that, okay? But if you were like, okay, well, let me try 8. 432 divided by 8 is 54. So what you could have done, I'll try to do this in another color, is you could have said, okay, oh, this is going to run out. You could have said, all right, let's turn this into the cube root of 8 times the cube root of 54. And the cube root of 8 is 2, but we want to make sure that 54 doesn't have any other perfect cubes in it. And we might see now, oh, 54 is 27 squared, so or 27 times 2. So I can break 54 down into 27 and 2, the cube root of 27 and the cube root of 2. The cube root of 27 is 3, and we're left with that cube root of 2. So notice, even if you don't find the biggest power that goes into the radicand, we can still get that final answer, okay? So let's talk about letter C. We have the 4th root of 10 over the 4th root of 27. Before, what we did is we just multiplied by like the radical itself to cancel it out. That's not going to work. What I'd like you to do in these problems is if you can write the number under the radicand, the radicand, if you can write the radicand as a power, I'd like you to do that. So let's rewrite 27 as 3 cubed, okay? In order for us to get this, like to get rid of the radical in the denominator, we need to be able to take the 4th root of something. So in your head, you think to yourself, oh, I would be able to take the 4th root of 3 to the 4th, because the 4th root of 3 to the 4th would just be 3, okay? We have 3 cubed right now. We only need one more of those in order to make that 3 to the 4th that we needed. So we had 3 cubed. We want 3 to the 4th. We only need 3 to the 1st in order to get there. So that means that you're going to multiply both your numerator and denominator by the 4th root of 3. Here, because the index is the same, we can multiply this together and we can change that into the 4th root of 30. And then our ultimate goal was to get rid of this radicand. And again, the 4th root of 3 to the 4th is 3. We could then see if any 4th roots go into 30, but we can see that like 4th roots are numbers like 16, and that's not going to go into 30, so that's about it. That's all you can do. Just like you can only add like radicals, like square roots, the same thing is true here. We can only add radical expressions with the same index and radicand. So if we have 7 times the 5th root of 12 minus the 5th root of 12, remember there's really like a 1 that's here. So we would subtract 7 minus 1 to give us 6 times the 5th root of 12. And that's it. Here we can't add these because they're not like radicals. So what we could try to do is break down the 4th root of 405. So let me look at my chart to look at some 4th roots. One of my 4th roots is 16. I don't think that's going to go into 405. Another 4th root is 81. Well, let me see, maybe that'll work. 405 divided by 81, and it goes in 5 times. So what I'm going to do is I'm going to bring the 2 down, and I'm going to break 405 down into 81 and 5. Now the 4th root of 81 is 3. And so this really turns into 6 times the 4th root of 5. So now let's see, maybe we could break 80 down. So again, we look, and one of our 4th roots is 16. I think 16 goes into 80. Hooray, it does. We can break the 4th root of 80 down into the 4th root of 16 times the 4th root of 5. The fourth root of 16 is 2. And then I'll just bring it down. And I see that we have 6 times the fourth root of 5 plus 2 times the fourth root of 5. Hooray, we have like radicals, so we can just add the coefficients to make 8 times the fourth root of 5. Let's do the same thing in letter C, but this time, because our index is 3, we're going to be looking for perfect cubes. So 1 perfect cube is 8. That's not going to go into 81. What about 27? And we can see that I can break 81 down into 27 times 3. So the cube root of 81 is really like 3 times the cube root of 3. When I look at the cube root of 24, I notice that 8's a cube root, and 8 will go into 24. I can break 24 down into 8 and 3. So the cube root of 24 becomes the cube root of 8 times the cube root of 3. The cube root of 8 was 2. And now that I've simplified each of the radicals separately, I see we now have like radicals, and I get 1 times the cube root of 3, or just the cube root of 3 is the answer. Okay? So break down those radicals. These are my favorite because I think they're relatively doable. Okay. So the properties of rational exponents and radicals can also be applied to expressions. Because a variable can be either positive, negative, or 0, sometimes absolute value is needed when simplifying a variable expression, but we're going to assume all variables are positive for our examples. This becomes an issue in pre-calc. I know the pre-calc teachers have come back to talk to me about that, but all the Algebra 2 and Trig teachers are assuming that all variables are positive, so you won't have to worry about the absolute value stuff if you look it up online or something, okay? So in example 6, we want to simplify it, and we're going to deal with the variables instead. And so in example A, we have the fourth root of 625z to the 12th, and we're going to think about breaking that down just as the fourth root of 625 and the fourth root of z to the 12th. Okay? If we look at our perfect square chart, we see that 625 is a perfect fourth. The fourth root of 625 is 5. And I want to teach you a little trick about when you have an index and you have a variable raised to a power. Okay? Again, so this is when you have an index and an exponent within the radical. What you can think about doing is you can think about dividing this value by the index, okay? So I'm going to write it like this: exponent under the radical, and you think about dividing it by the index. The reason that that's legal is because technically this root, this fourth root, is really like raising it to the 1/4, okay? So I'll show you how that works. So I want you to think about taking 12 divided by 4. Doesn't that give you 3? And it turns out that the fourth root of z to the 12th is going to be z cubed. I want you to think about why that's legal. Based on what we talked about the other day, isn't the fourth root the same as raising it to the 1/4? And so really we're taking 12 to the first, or sorry, 12 over 1 times 1/4, which gives us 12 over 4, which gives us z cubed. So that's why this little trick works, is because that index is really a rational exponent, okay? So that's the science behind why that works. Let's maybe do another one like that. Let's jump to example C with this radical here. So we have the 6th root of r to the 6th over s to the 18th. I would maybe rewrite that as the 6th root of r to the 6th over 6th root of s to the 18th. So we can play that game again. 6 goes into 6 once, so that's just r. 6 goes into 18 3 times, so that gives me s cubed. That's it. Let's practice one more time in example E. You can't take 3 into 6. 6 is not an exponent, and there aren't any perfect cubes that will go into 6. So we're going to leave that cube root of 6 part alone. Okay? Now let's take 3 into 4. 3, so 4 divided by 3 is 1, right? So 3 goes into 4 once, which means on the outside I can take out an x to the first. But we have 1 left over. 3 goes into 4 once with 1 left over. That 1 left over goes under the radical. Now let's take 3 into 9. 9 divided by 3 is 3. So that exponent of 3 goes on the outside with the y. 3 goes into 9 evenly, so I don't have any y's left on the inside. Now let's take 3 into 14. So 3 goes into 14 4 times. So that means that my exponent for z on the outside can be z to the 4th. But there are 2 left over, so those 2 left over go on the inside. And that's how we can simplify. And of course, we don't need that exponent of 1 there. But that's how you can simplify expressions with the radicals with different indices. Okay. Let's pop back up to b. Again, we'd want to apply this 1/5 to each base. So we'd have 32 to the 1/5. And remember, 32 to the 1/5 is the same as the 5th root of 32, which is just 2. 1/5 times 5 is just 1. And 1/5 times 30 is 6. So that just gives us 2mn to the 6. All right. In letter D, what I might start doing is just moving the exponents around and maybe making common denominators as I go. So if I were to change this, I'll keep the 56 and 7 for right now. But I notice that these a's, like this is a to the 1st and a to the 5/6, I'm going to have to subtract. So maybe I want to write that I'm going to think about a to the 1st as a to the 6/6. Then I have this b to the 3/4. Then that c to the -3rd is going to pop up as c cubed. And then I can simplify. 56 over 7 is 8. 6/6 minus 5/6 is 1/6. So I have a to the 1/6. And then there's really nothing I can do to the b to the 3/4 and c cubed. So that ends up being my answer for 6D. So let's talk about 6F. I can rewrite this as the 7th root of p to the 8th over the 7th root of q to the 5th. I can use that rule we talked about. 7 goes into 8 once, so I have p to the 1st on the outside. But there's 1 left over, so I have p on the inside. But here 7 doesn't go into 5, so I'm going to leave that as the 7th root of q to the 5th. Now the issue is that we have a radical down here. We want to get rid of it. And what we want is we want something that we can take the 7th root of. So in our head, what we do is we're thinking, like, I could take the 7th root of q to the 7th, right? So I have q to the 5th. What do I need to make it q to the 7th? Well, I would need 2 more. I would need q to the 2nd. So whatever I do in the denominator, I have to do to the numerator. So in the numerator, I still have that p. And then I have the 7th root of both p and q squared. And I'm multiplying, so of course I can multiply those together. And then in the denominator, now I have the 7th root of q to the 7th. And I can see now that it's legal for me to take the 7th root of q to the 7th to just get q. And so then I end up with p times the 7th root of pq squared all over q is the final answer. It's intense, right? Okay. So now in example 7, we're going to do what we did in example 5, but involve variables also. We want to make sure we can only add or subtract like terms. And here notice that we have like terms when we look at the cube root of u. So we would just take 18 minus 11 to make 7 times the cube root of u. Notice here we have like terms. A to the 4th, b to the 2/3 is the variable portion of both of those. So I can just take 15 plus 8 to make 23, a to the 4th, b to the 2/3. But then I look at c, and I'm like, oh poop. We do not have like radicals. Well, let's try to simplify them. If I look at the fourth root of 5s to the 7th, 5 doesn't have any fourth roots in it. 5 is too small. But I notice I can use that little exponent trick with this 4 and 7. So I'll write my 10 that's on the outside. I know that I'm going to keep 5 under there because there's no fourth roots that go into 5 other than 1. And because these are exponents, 4 goes into 7 once. So that means I can take out an s to the first. And then there are 3 left over, so I have s cubed that's left. Okay, so now let's try that over here. I'm going to leave the s on the outside, but then I'm going to try to take the fourth root of 80, s cubed. Now when I think about fourth roots, 16, we saw earlier, goes into 80. So I can think about breaking that down into 16 times 5. And then we also have that fourth root of s cubed that's there. Again, we chose the fourth root of 16 because that becomes 2. But we don't write s2, we write 2s. And then again, 4 doesn't go into 3. That's kind of why I just kept that. But let's just keep it as one radical when we're trying to simplify that term. All right, so I have 10s times the fourth root of 5s cubed minus 2s times the fourth root of 5s cubed. That 2 is what that cubed is for. Anyway, so we can see we have like radicals, the fourth root of 5s cubed. So I can take 10s minus 2s to make 8s times the fourth root of 5s cubed. So those are some examples, you guys. That's what we wanted to work on through this in class, because notice none of these problems are attacked in exactly the same way. You just got to have all these things in your toolbox that you're working towards. All right? Thanks for tagging along. We'll see you soon.